Hello everyone, this is 7th video. Now the theorem, let f be a non-negative function which is integrable over a set E. Then we have to show for given epsilon greater than 0, there is a delta greater than 0 such that for every set A subset of E with measure of A less than delta, we have integral of f over A is less than epsilon. Once again, see what is given to us. F non-negative function, may be bounded, may be unbounded, okay, and it is integrable, means integral of f over E is finite. Then we always have a subset of E with measure of A very small, then the value of integral of f over that set will be also small. Now the first case, let's suppose f is bounded function. If f is bounded function, then clearly mod of fx will be less than equal to capital M for all x belonging to E and for some number capital M. So if we choose any set capital A with measure of A less than delta, and delta we can set delta to be epsilon by capital M for some given epsilon greater than 0, then value of integral f over A clearly less than equal to, since our f is bounded, so you can replace f with capital M. So you will get integral of 1 over A. So this is nothing but the measure of A. And measure of A is less than delta. So you can substitute the value of delta over here. It is epsilon by M. So capital M will be cancelled out. You get only epsilon. So whenever your function is bounded, integral of f over the set A is less than epsilon, where the measure of A is very small. So this result holds trivially in case when f is bounded. So next we assume that f is an unbounded function on the set E. For this we define a sequence of functions like it will be fx if your fx is less than equal to n, it is n if your fx is greater than n. Means if your function is bounded and its value is less than equal to n, then you take this to be fx only, and if this value is greater than n, then you can take fnx to be n. Now just see, when you take n to be 1, so f1x is defined like this. If fx is less than equal to 1, then your f1x is fx, otherwise its value is 1. Your n is 1 here. The next, n is equal to 2, your f2x will be what? If the value of fx is less than equal to 2, then you consider this to be as fx, otherwise you take it as 2. So clearly f1x is less than equal to f2x, right? Our f2x is bigger because either it is 2 or it is fx, right? If it is fx, in f1 also it is fx. But if your fx is greater than 1 in case of f1x, then its value is 1. However, in f2x, its value is 2. So that is the bigger one. So clearly this is increasing sequence. And also when you find the limit n going to infinity, it is going to fx. Why? Because the value of this sequence is fx whenever fx is less than equals to n. So when you take infinity, its value is always fx. Greater than infinity, its value is infinity, right? But this is not included in the domain. So limit n going to infinity fnx is nothing but your fx. So in case of unbounded function, we will define a sequence of functions over the set E like this. And this sequence is converging to fx. So now observe that fnx is increasing, bounded, and it converging to f on E. So what we observe that fn is increasing, it is bounded, and it converges to f on E. So we can apply monotone convergence theorem over here. So by monotone convergence theorem, integral of f over E is same as that the limit integral of fn over E. Okay, so now by the definition of limit, we get for given epsilon greater than 0, there is capital integer n such that integral of fn over E will be greater than integral of f over E minus epsilon by 2. Now why? Because in monotone convergence theorem, we know that integral of f over E is same as that the limit integral of fn over E. So this is nothing but the supremum and infimum also. If integral of f is the supremum, we subtract some number from it, then this is not the supremum. We always have some value of integral which is greater than this number. So by the definition of limit, we can have for some given epsilon there is integer capital N such that this integral is greater than this minus epsilon by 2. Now we can take this to be this side. So integral of f minus fn over E will be less than epsilon by 2. And given that f is an integrable function, so the value of integral of f over E is finite, right? So if we choose delta to be less than epsilon by 2 capital N and measure of A is less than delta, then integral of f over A can be written as integral of f minus fn plus fn over A, right? And which is further less than this integral over E. Rather taking A, it is over E. Since A is a subset of E, so it will be less than this. Plus, now over the set A, what is the value of fn? It will be less than equal to capital N. Why? Because we choose fn to be in such a way either its value is fx or its value is n. So in any case it is less than equal to n because our fx is less than equal to n, right? So we can replace here by capital N. So we get one integral of 1 over the set A, which is nothing but the measure of A. And we choose measure of A to be less than epsilon by 2n, so you can substitute over here. So over n and n will be cancelled out and you will get epsilon by 2. And the value of this integral is also less than epsilon by 2. So you can substitute over here. So epsilon by 2 plus epsilon by 2 is nothing but epsilon. This thing we have to show. So whenever we have an integrable function or and non-negative function, right, over a set E, then we always have A as a subset of E such that measure of A is very very small, then the value of integral over A is also very very small. So now we evaluate the integral of the function this defined by the sequence this. So we will use the previous theorem to evaluate this integral. Now just see here, your function is non-negative, okay, and you can show that this function is measurable also. So this function is unbounded. Why it is unbounded? Because when you take x tending to 0, its value is approximately infinity. So this is unbounded, this is non-negative, this is measurable. It is defined on the interval 0, 1, which is also measurable. So by previous theorem, we can define a sequence fnx of the functions on the interval 0, 1, where fnx is fx whenever fx is less than equal to n, and it is n otherwise. So now you substitute the value of fx over here. Our fx is 1 over x to the power 1 by 3. So fnx is what? It is fx. If your fx, so write fx over here, it is 1 over cube root of x, is greater than is less than equal to n. So when you simplify this, you will get x is greater than equal to 1 over n cube. So whenever x is greater than equal to 1 over n cube, the value of the sequence is this one. And whenever your x is less than 1 over n cube, the value of the function is n. So clearly this sequence is non-negative, increasing, right, and bounded by n. So by previous theorem, we can find out the value of integral of f over 0, 1 by taking the limit integral of 0 to 1 of fn. This is by monotone convergence theorem. So now you can split this integral from 0 to n to the power minus 3, 1 over n cube. That means the value of function is n, otherwise its value is 1 over x to the power cube root. So you can substitute over here. So now you integrate this. This is nothing but n times x. When you put the limit, you will get 1 over n square. Similarly, the integration of this and substitute the limits, you will get this thing. So when you take n tending to infinity, this is 0, this is 0, you will get 3 by 2. Since the value of integral of f over e over this set is finite, so you can say your function is integrable. Hence, in this way, we can find out the value of integral of f whenever your f is unbounded. So we can define a sequence fn and we can apply monotone convergence theorem and we can find out the value of integral. Now the remark, clearly this integral is an improper Riemann integral. Why? Because the value of this integral over 0 is approximate infinity. Integral, the value of function. At 0 it is infinity, so this is improper Riemann integral. However, it is Lebesgue integral, perfectly Lebesgue integral. Why? Because it is the integral of an unbounded function, and in case of Lebesgue integral, integral of unbounded function is defined. But you can find out the value of this improper Riemann integral. You just integrate it, substitute the limits, you will get the value is 3/2, which is same as that here. So we observe that the value of integral in each case is same, which is 3/2. Thanks.